Welcome to the Deep Dive. Our mission today, well, it's a big one. We're diving into the physics behind the 2025 Nobel Prize.
That's right. Awarded jointly to John Clark, Michel Devoret, and John Martinis.
And the citation itself sounds pretty intense. For the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit.
It does sound intense, but what it really means, for you listening, is kind of mind-bending. They showed that the absolutely bizarre rules of quantum mechanics, the stuff governing tiny electrons and atoms.
Yeah, the really small-scale stuff.
Exactly. They showed those same rules apply to something, well, big enough to see. A chip maybe a centimeter across, something you could, almost get your grubby fingers on.
Which totally challenges how we normally think about physics, doesn't it? Big things follow classical rules, small things follow quantum rules.
That was the standard picture, for sure. For almost 100 years, the idea was quantum weirdness just fades away as things get bigger. It gets washed out by noise, by interacting with the environment.
But this experiment, this prize, it's about a superconducting circuit. We're talking billions and billions of particles in there.
Billions. Yet they managed to show this whole collection of particles could act like a single, unified quantum object. A bit spooky, really.
Like a giant artificial atom built on a chip.
That's a great way to put it. And the challenge, how do you even begin to prove that?
Yeah.
How do you isolate something with that many parts so perfectly that its collective behavior is purely quantum, not just some random thermal jiggling?
It sounds like it needs isolation on a whole different level, extreme engineering.
Oh, absolutely. It pushed the boundaries of precision. Okay, so let's unpack this whole thing. Where should we start? Maybe with the core idea, tunneling itself.
Yeah, let's do that. Let's revisit the basics. Quantum tunneling. It popped up pretty quickly after quantum mechanics got going in the 1920s, right?
Right after Schrödinger came up with his famous equation in 1926, people solving it started noticing something strange. The math showed that the wave function, the thing describing the particle...
The probability wave.
Exactly. It didn't just stop dead at a potential barrier if the particle didn't have enough energy to get over it classically.
Okay, so classically, think about throwing a marble at a hill. If it doesn't have enough speed, enough energy, it just rolls back down, right? Every single time.
Every time. But quantum mechanically, the particle's wave function actually penetrates into the barrier. It decays, gets smaller exponentially, but it's still there inside the forbidden region.
And if the barrier isn't too thick?
If it's thin enough, there's still a tiny bit of that wave function left on the other side, a non-zero amplitude.
Which means there's a chance, a probability, the particle can just appear on the other side.
Bingo. It tunnels through. Even though it never had the energy to actually climb over the hill, it violates classical intuition completely.
But it's not just a weird theoretical quirk. You mentioned alpha decay earlier. Tunneling is essential for that.
It's the textbook example, really. Before quantum mechanics, things like the really long half-lives of some radioactive nuclei were a total mystery. Why did they take so long to decay?
So an alpha particle is trapped inside the nucleus by this strong energy barrier.
A very strong barrier. Classically, based on its energy, it should never escape. But George Gamow, back in 1928, realized it must be tunneling out.
Ah, so the probability of tunneling determines how quickly it decays.
Precisely. It explains why radioactive decay is probabilistic and why different elements have vastly different half-lives. It depends on the height and width of that barrier for the alpha particle.
And the other really big example, the sun, fusion.
Yeah, stellar fusion. It's kind of amazing. But the core of the sun, while incredibly hot, isn't quite hot enough for protons to just smash together classically. They repel each other really strongly, the Coulomb repulsion.
So they get close, but not quite close enough to fuse based on just temperature and pressure.
Right. That final little distance, that last bit of the barrier, they overcome it by quantum tunneling. Without tunneling, our sun wouldn't work the way it does. Stars wouldn't shine. It's fundamental.
Okay, so tunneling is real. It's important. And it even got Nobel recognition before, right? Back in '73.
It did. Leo Esaki and Ivar Giver shared part of the 1973 prize for experimentally seeing electron tunneling. Esaki in semiconductors, Giver in superconductors.
So wait, if Giver saw tunneling in superconductors back then, what makes the work by Clark, Devoret, and Martinis, like 15 years later, such a big leap? Why another prize for tunneling?
That's the absolutely crucial difference. Esaki and Giver were looking at the tunneling of single electrons, or quasi-particles. Individual quantum particles doing their thing.
Okay, still microscopic.
Definitely still microscopic. Their work was huge, mind you. It confirmed predictions from BCS theory about the energy gap in superconductors, and BCS theory itself had just won the Nobel the year before, in '72.
Right. So what connects that to the 2025 prize then?
The connection is the other person who shared that 1973 prize, Brian Josephson. Josephson wasn't looking at single electrons. His theory predicted something much bigger.
He predicted tunneling related to Cooper pairs, didn't he?
Exactly, Cooper pairs, the fundamental unit of superconductivity.
Okay, let's dig into that. What's special about a Cooper pair? Why does it allow for this macroscopic quantum stuff?
Well, it comes back to BCS theory, Bardeen, Cooper, and Schrieffer. Electrons are fermions, meaning they normally obey the Pauli exclusion principle. They can't be in the same state. They sort of repel each other in that quantum sense.
Okay.
But in certain materials at very low temperatures, electrons can interact with the vibrations of the crystal lattice in a way that allows them to form pairs. Cooper pairs.
And pairing them up changes their fundamental nature.
It does. Two fermions together, the electrons, act like a single composite boson. And bosons are totally different. They love being in the same quantum state. They can all pile into the lowest energy level together.
Ah, like a Bose-Einstein condensate.
Precisely. The superconducting state, the BCS ground state, is a macroscopic Bose-Einstein condensate of these Cooper pairs.
Yeah.
It fills the entire piece of superconducting material.
So instead of billions of separate electrons, you have billions of pairs all acting in perfect unison.
In perfect unison, they share a single collective quantum state. We can describe the behavior of this entire condensate, all those billions of pairs, with just one complex number called the order parameter, or think of it as a single shared effective wave function.
Wow. So the whole circuit has one wave function describing all the pairs together.
That's the conceptual leap. The entire system behaves coherently, like one giant quantum particle spread throughout the circuit.
And to see if that giant quantum particle can tunnel, you need the right kind of barrier. Which brings us back to Josephson's idea.
The Josephson junction. It's the perfect device for this. It's incredibly simple in concept. Just two pieces of superconductor separated by a very, very thin insulating layer, maybe just a few atoms thick.
Like a tiny gap.
A tiny gap. And Josephson predicted that the Cooper pairs, this coherent quantum fluid, could tunnel across that insulating gap together without any resistance. That leads to a current flowing even with zero voltage across the junction.
Okay, so that's the macroscopic tunneling Josephson predicted, the whole condensate flowing across.
Yes. It's the coherent tunneling of the entire macroscopic quantum state, not just individual electrons popping across one by one like in J. Aver's experiments.
All right, so the pieces are there. We have a macroscopic quantum thing, the Cooper pair condensate, and a specific barrier, the Josephson junction. The big question then becomes, can the system do more than just flow? Can it show really weird quantum effects like superposition or this macroscopic quantum tunneling, MQT?
And that's where we run right into the biggest conceptual hurdle in quantum mechanics, the sheer absurdity of scale, which of course makes everyone think of
Schrodinger's cat.
Schrodinger's cat. The poor cat, simultaneously alive and dead, is fate linked to a single quantum event like an atom decaying or tunneling.
Schrodinger didn't actually think that could happen, did he? He meant it as a criticism.
Exactly. It was a reductio ad absurdum. He was pointing out how ridiculous it seemed to apply the rules of quantum superposition directly to large, everyday objects.
Yeah.
And for decades, the consensus was he was basically right.
Why? Because of decoherence?
Decoherence. The idea is that any real-world macroscopic system is constantly interacting with its environment. Air molecules bouncing off it, photons hitting it, vibrations, you name it. These interactions effectively measure the system constantly.
And measurement collapses the superposition.
Right. The bigger the system, the more ways it can interact with the environment, and the faster any delicate quantum superposition just falls apart into a definite classical state. For something cat-sized, this happens practically instantly.
So the challenge for Clark, Deveray, and Martinis wasn't just making a macroscopic quantum state superconductors kind of do that already with the condensate.
Right, the condensate itself is robust.
But the challenge was keeping a delicate superposition or enabling a sensitive process like tunneling in that macroscopic state long enough to actually observe it, winning the race against decoherence.
That's the core of it. And it helps to distinguish between two kinds of macroscopic quantum states. The first kind is robust, like the superconducting condensate itself or the light in a laser beam. You can think of its wave function as a product of the states of its parts. If you poke one part, the rest are mostly unaffected.
Okay, stable.
Stable. But the state needed for MQT, or for quantum computing later on, is the fragile kind, the cat state. It's a superposition of two macroscopically distinct states. Like, imagine all the Cooper pairs simultaneously flowing clockwise and counterclockwise around a loop.
So if you measure anything about the flow anywhere.
The whole thing collapses instantly.
Yeah.
All billions of pairs snap into either clockwise or counterclockwise, not both. These states are incredibly sensitive to any environmental disturbance.
Okay, so could you actually isolate a system, even a superconducting circuit, well enough to see this fragile quantum behavior before the environment killed it?
That was the million-dollar question. And the person who really pushed this, theoretically, was Anthony Leggett.
Right, Leggett, another Nobel laureate himself later on. What did he propose?
Back in 1978, Leggett, who was a deep thinker about quantum mechanics at macroscopic scales, especially superfluids, posed the question directly. Could we make a kind of mini Schrodinger's cat state using superconducting circuits? Could we see macroscopic quantum tunneling, MQT?
And he thought superconductors were the place to look.
He argued they were the best bet, precisely because they are superconductors. Zero electrical resistance suggests they have intrinsically very weak coupling to the things in the environment that cause energy loss or dissipation.
Less friction, basically.
Less friction. So he reasoned if you could cool these circuits down to incredibly low temperatures, we're talking millikelvin, thousands of degree above absolute zero maybe, just maybe, you could slow down decoherence enough to actually see MQT happen.
But it wasn't just maybe it works. Theory had to grapple with the fact that the isolation wouldn't be perfect, right? There would still be some friction, some damping.
Absolutely crucial point. Leggett, working with Anupam Caldera, developed the theory for how MQT would be affected by this residual dissipation. What they showed was critical for the experiments.
What did they find?
They found that even a small amount of dissipation, a weak coupling to the environment, would suppress the rate of quantum tunneling. If the dissipation was too strong, the system escaping its trapped state would look just like classical thermal activation, like it was just being kicked out by random heat energy, even at low temperatures.
Ah, so the quantum tunneling could be masked or even completely wiped out by leftover noise or friction.
Exactly. It meant that any experiment claiming to see MQT had to do two incredibly hard things. First, achieve unprecedented levels of isolation to minimize that dissipation. Second, they needed a way to prove that what they were seeing was truly quantum tunneling, and not just some leftover classical effect they hadn't managed to eliminate. They needed to measure the system's parameters independently.
The bar was set incredibly high. It wasn't just about seeing something happen at low temperatures.
It had to be quantitatively shown to be quantum, which leads us directly to the heroic experimental work done at Berkeley.
Right. Clark, DeVray, and Martinis. They tackled this challenge head-on using actually a fairly simple system conceptually, just a single Josephson junction biased with a current.
Simple concept, incredibly difficult execution. And they used a brilliant analogy to visualize the physics, the tilted washboard potential.
Okay, the washboard. Let's break that down. It helps visualize this complex quantum behavior in terms of something more familiar, like a particle moving.
It does. In this analogy, the thing that's moving isn't a real particle, but a collective variable representing the whole quantum state. It's the phase difference, usually written as delta, across the Josephson junction.
So the position of this fictitious particle is the phase difference, the degree of freedom for the whole condensate.
Precisely. And its mass, or inertia, is related to the electrical capacitance of the junction. Just like mass resists changes in velocity, capacitance resists changes in voltage across the junction.
Okay, so we have a particle, the phase delta with mass, related to capacitance. What creates the washboard potential it moves in?
That comes from the fundamental physics of the Josephson junction itself.
Yeah.
Its current phase relationship is sinusoidal. That naturally creates a potential landscape that looks like a series of repeating hills and valleys, like a washboard.
And the tilt?
The tilt comes from the bias current they apply to the junction. Pushing current through it is like tilting the whole washboard.
And when you tilt it, the valleys become potential traps for the particle.
Exactly. If the bias current dollar is less than the junction's critical current I dollars, the maximum current it can carry without resistance, the tilted washboard potential has these wells, these local minima. Our fictitious particle, the phase delta, can get trapped in one of these wells.
And being trapped in a well corresponds to the real physical state of
the superconducting state with zero voltage across the junction. Current is flowing, but there's no resistance, no voltage drop. This is a metastable state they want to study.
Okay, so the whole experiment is about watching this fictitious particle escape from the well. Classically, if it's cold enough, close to absolute zero, there's no thermal energy to kick it out. It should stay trapped forever, shouldn't it?
Classically, yes, trapped forever. But quantum mechanically, the particle's wave function leaks through the barrier, the hill part of the washboard next to the well,
It can tunnel out. Macroscopic quantum tunneling.
MQT. And when it tunnels out, the phase difference delta is no longer trapped. It starts running down the tilted washboard. Physically, this means the junction switches abruptly from the zero voltage state to a state with a finite, measurable voltage, V dollars wallers.
So the experiment boils down to measuring when that voltage suddenly appears.
Exactly. They would slowly ramp up the bias current, tilting the washboard more and more, making the barrier thinner and the well shallower, and measure the exact current value at which the junction switched to the voltage state.
And they'd have to repeat this thousands of times to build up statistics. Thousands and thousands of times. To get a probability distribution, what's the chance of it escaping at this current versus that current?
Which brings us back to that huge problem, noise. How did they know the escape wasn't just caused by some tiny bit of heat or electrical noise kicking the particle over the barrier rather than tunneling through it? Other groups had seen escape rates flatten out at low temperatures, but the ambiguity remained.
That ambiguity was the killer. This was the early 80s, and people saw this saturation, which could have been MQT taking over from thermal activation below a certain crossover temperature as predicted. But it could also have just been that their equipment wasn't cold enough everywhere, or that some stray microwave radiation from warmer parts of the setup was leaking down and heating the junction just enough to cause classical escapes.
So how do you shield something that effectively? We're talking milli-Kelvin temperatures. Any tiny leak of energy is significant. This is where the Berkeley group's experimental genius really shone. They became absolutely obsessed with thermal isolation and noise filtering. They designed and built a measurement setup with painstaking care. The key was an incredibly sophisticated filter chain for all the electrical leads going down to the junction in the cryostat.
How good were these filters?
We're talking over 200 decibels of damping for frequencies from about 0.1 up to 12 gigahertz. That's the range where stray microwave photons could potentially excite the junction.
Okay, 200 dB, that's reducing the noise power by a factor of 10 to the power of 20. That's astronomical isolation.
It's almost unbelievable. They used newly developed copper powder microwave filters and were incredibly careful about thermally anchoring everything, making sure every component was truly at the base temperature.
But even with that incredible filtering, how did they definitively prove it was MQT and not some minuscule remaining noise source? That's where the Caldera-Leggett theory connection comes in, right? The need for independent verification.
Precisely. Just filtering wasn't quite enough to silence the critics. The absolute masterstroke was their use of resonant activation. This technique allowed them to measure the junction's key parameters independently of the MQT escape process itself.
Okay, resonant activation. How did that work?
They added a separate, very weakly coupled microwave line to inject tiny amounts of microwave radiation at specific frequencies directly onto the junction. They did this at temperatures slightly above the crossover temperature, where escape was definitely classical thermal activation.
Why above?
Because there, the particle's just jiggling around at the bottom of the well due to thermal energy. If you send in microwaves at just the right frequency, the frequency corresponding to the particle's natural oscillation frequency at the bottom of the well, called the plasma frequency, you get resonance.
Like pushing a swing at just the right moment.
Exactly like that. The particle absorbs energy efficiently, its jiggling amplitude increases dramatically, and it escapes the well much more easily. By tweaking the microwave frequency, they could find the peak response that told them the plasma frequency.
Okay, so that gives them one parameter. What about the damping, the friction?
The width of that resonance peak is directly related to the damping or the resistance experienced by the phase particle in the well. A sharper peak means less damping. A broader peak means more damping.
Ah, brilliant. So by doing this resonant activation measurement in the classical regime, they could experimentally determine the junction's plasma frequency related to capacitance and critical current, and its damping resistance, the exact parameters needed for the Caldera-Leggett MQT theory.
Precisely. They measured the parameters independently. No guesswork, no fitting them later to make the MQT data look good. They locked those parameters in.
And then they cooled the system down below the crossover temperature into the regime where MQT should dominate.
Then they went cold. They measured the escape rate distribution purely by ramping the bias current with no microwaves applied, and they compared that experimental data to the predictions of the Caldera-Leggett theory using the parameters they had just independently measured.
And the result?
Perfect agreement. The measured escape rates matched the theoretical quantum tunneling rates quantitatively, with no free parameters left to adjust. That was the smoking gun. It proved, beyond reasonable doubt, that they were observing the quantum tunneling of a macroscopic degree of freedom. Billions of Cooper pairs acting in unison, tunneling through a potential barrier.
That quantitative agreement is just scientifically beautiful. It nails the first part of the Nobel citation, macroscopic quantum tunneling. But they went further, didn't they? They also proved energy quantization.
They did. This was arguably just as important. It showed that this macroscopic particle, the phase difference, didn't just tunnel randomly. It behaved like a true quantum object with discrete quantized energy levels, just like an atom.
How did they show that? Did they use the microwaves again?
Yes, they essentially repurposed the resonant activation setup to perform microwave spectroscopy on the macroscopic quantum state.
Spectroscopy, like analyzing the light frequencies absorbed or emitted by atoms to see their energy levels?
Exactly the same principle,
Yeah.
but applied to their artificial atom, the junction. They kept the junction cold in the MQT regime. Then they irradiated it with microwaves at a fixed frequency, say 2 gigahertz.
Okay.
And they slowly ramped the bias current dollars.
Huh?
As they ramped the current, the shape of the washboard well changed, and therefore the energy spacing between the quantum levels in the well also changed.
Ah, so they're tuning the energy levels by changing the current.
Precisely. They looked for specific current values, where the energy difference between the ground state, the lowest level in the well, and one of the higher excited states precisely matched the energy of the incoming microwave photons, determined by Planck's constant times the frequency, HSF.
And if the energy matched?
The phase particle would absorb a microwave photon and get promoted to that higher excited state.
Okay, but how does that help them see quantization? How does being in an excited state affect the tunneling?
This relies on a concept from quantum mechanics called the WKB approximation. Basically, it tells you the tunneling probability depends exponentially on the thickness and height of the barrier the particle sees.
Right.
A particle in a higher energy state is physically closer to the top of the barrier in the washboard potential. It effectively sees a thinner barrier compared to a particle in the ground state.
And a thinner barrier means it's much easier to tunnel through.
Much easier. The tunneling rate increases dramatically. So when they hit a resonance, when the microwave frequency matched an energy level spacing and promoted the particle, they saw a sharp increase in the escape rate at that specific bias current.
They could see distinct peaks in the escape rate corresponding to exciting the system to different energy levels.
Exactly. They clearly observed enhanced tunneling not just from the ground state, but peaks corresponding to tunneling out of the first, second, and even third excited states.
Oh.
And crucially, the specific bias currents where these peaks occurred allowed them to calculate the energy spacings. Those measured energies perfectly matched the predictions from solving the basic Schrödinger equation for a single particle in the tilted washboard potential.
So it proved the macroscopic phase difference behaves exactly like a textbook single quantum particle, complete with discrete quantized energy levels.
Conclusively, they had demonstrated both MQT and energy quantization in a macroscopic electrical circuit. It was a landmark achievement.
This really feels like the moment where quantum physics stopped being just about understanding nature and started being about engineering nature. They built an artificial quantum system you could control.
That's a perfect way to phrase it. They essentially created an artificial atom, or maybe a macroscopic nucleus with wires attached. It fundamentally changed the game.
How is it different from other things, sometimes kind of macroscopic quantum phenomena, like lasers or just regular superconductivity?
In lasers, or conventional superconductors, you have a macroscopic effect arising from the collective behavior of many microscopic quantum parts. But the overall state is usually robust, like that product state we talked about. Here, Clark, DeVray, and Martinez created a system where a macroscopic variable, the phase difference, involving billions of electrons itself, behaved as a single quantum entity, exhibiting delicate superposition, implied by tunneling, and quantization, leading to a macroscopic outcome, the voltage switching. And crucially, it was highly controllable with currents and microwaves.
And that controllability, that engineered quantum system, must have immediately caught the attention of people thinking about quantum computing.
Oh, absolutely. This work laid the essential groundwork. When Peter Shor came up with his algorithm in 1994, showing a quantum computer could factor large numbers exponentially faster than classical computers, the race was on to actually build qubits controllable quantum two-level systems.
And superconducting circuits, thanks to this foundational work, were prime candidates from the start.
They were. Let's trace that evolution a bit. The very first superconducting qubits really tried to harness the quantum behavior of charge.
Like the single Cooper pair box, the SCPB.
Exactly. In the late 90s, researchers managed to build these tiny boxes and showed they could put the system into a superposition of having 0 extra Cooper pairs in the box versus having 1 extra Cooper pair.
Okay.
They saw the first coherent oscillations between these states. Proof of principle.
But you hear those early coherence times were incredibly short, like nanoseconds short.
Frustratingly short, just a few nanoseconds, yeah. The quantum state vanished almost instantly due to noise, especially charge noise. You can't do much computation in a few nanoseconds.
So improvements were needed. What came next?
Well, one approach was the phase qubit. And interestingly, the phase qubit directly used the physics demonstrated by Clark, de Vere, and Martinis. Its quantum states were related to the phase difference delta trapped in the watchboard well, and its readout often involved MQT.
So they'd measure the qubit by basically seeing if it tunneled out of the well when prompted?
Pretty much. They'd put the qubit in a state, then apply a pulse that effectively lowered the barrier, and quickly measure if a voltage appeared indicating tunneling, which corresponded to, say, the one state. The 1985 MQT experiment became a qubit readout technique.
A direct lineage, but coherence times were still a limiting factor, right?
Still the main bottleneck. The huge leap forward came around 2004 with the development of circuit quantum electrodynamics, or CQED.
Okay, CQED. Sounds fancy. What's the core idea?
The core idea, pioneered heavily by groups including de Vere's and others, was to take the superconducting qubit, the artificial atom, and strongly couple it to a simple microwave resonator, like a tiny transmission line or cavity on the chip.
So the qubit talks primarily to this resonator.
Exactly. And the resonator then talks weakly to the outside measurement lines. This architecture does two amazing things. First, it provides a way to read out the qubit state without instantly destroying it, a technique called quantum non-demolition readout. You measure the resonator's frequency shift, which depends on the qubit state.
Crucial for error correction later on.
Absolutely. And second, by embedding the qubit in this clean, well-defined electromagnetic environment of the resonator, you shield it much better from all sorts of stray environmental noise.
Better isolation again.
Better isolation. CQED architecture dramatically increased coherence times, pushing them from nanoseconds into microseconds and beyond. It really enabled the field to start thinking about building larger systems.
Which leads us to the kind of qubit that dominates today.
The transmon qubit. Developed building on the CQED principles, the transmon is essentially an optimized version of that early Cooper pair box, but designed specifically to be insensitive to charge noise, which was a major killer of coherence.
How does it manage that?
By operating in a different parameter regime, using a large shunt capacitance. This makes the energy levels of the qubit almost independent of small fluctuations in background charge. It sacrifices some anharmonicity, how different the energy levels are, but gains massively in coherence time.
So the transmon is the workhorse in most of the big quantum computing efforts we see now at Google, IBM, Rigetti, etc.
It really is. So the legacy of that 1985 MQT and quantization discovery isn't just the fundamental physics, it's the entire technological pathway leading to today's state-of-the-art quantum processors.
It's not just qubits, though, is it? These circuits have become tools for other kinds of physics research.
Definitely. They've opened up whole new ways to study quantum optics, for example. You can achieve coupling strengths between artificial atoms and photons in these circuits that are incredibly hard or impossible to reach with real atoms and optical cavities.
Exploring new regimes of light-matter interaction.
Exactly. And people are using these highly coherent circuits as probes. They're coupling them to other larger systems to see if those systems also behave quantum mechanically. Things like tiny vibrating beams, micromechanical resonators, or even large collections of electron spins, pushing the quantum boundary outwards.
And you mentioned a really recent striking example using these circuits for fundamental tests.
Yeah, that 2023 Bell test experiment was remarkable. Using superconducting circuits, based on all this accumulated knowledge of isolation and control, housed in a giant 30-meter-long cryostat to get the necessary separation.
30 meters.
30 meters apart. And they performed a loophole-free test of Bell's inequality, confirming quantum entanglement and non-locality with engineered solid-state devices at an unprecedented scale. It just shows how this technology, born from proving MQT, continues to be at the forefront of fundamental discovery.
It really feels like they built this incredibly robust bridge between the microscopic quantum world and the macroscopic world we can engineer and control.
That's the essence of it. Clark, DeVray, and Martinis, through sheer experimental grit and ingenuity, took quantum mechanics from the blackboard in the domain of single atoms and proved it lived inside a tangible electronic circuit.
It wasn't just confirming a theory, it was demonstrating control, providing the actual hardware, the components, the cables and sockets, as the Nobel Committee put it, that were needed to build the next generation of quantum technologies.
Exactly. They gave us the first genuinely controllable macroscopic quantum systems. It moved us beyond just marveling at the strangeness of quantum mechanics or being limited by Schrödinger's thought experiment, and into the era of engineering with quantum mechanics.
Ole Eriksson, who chaired the Nobel Committee, made a great point. Isn't it wonderful that quantum mechanics, even after a century, keeps throwing up these surprises? It underpins not just atomic physics, but all our digital tech. And now it's fueling this whole new field of quantum engineering.
It really is astounding. Think about it. We started this discussion with Schrödinger, using his cat to illustrate the perceived absurdity of large-scale quantum effects.
Right. It was meant to show why it couldn't happen.
And now, thanks to the work of these laureates and those who followed, engineers are routinely designing circuits where those very principles, superposition in qubits, tunneling for readout, quantized energy levels are not absurdities, but essential engineered features of large-scale systems like the transmon.
We've normalized the quantum behavior of something you can hold in your hand, almost. Which leaves us with a final thought for you, our listener.
If we've managed to tame the quantum mechanics of a centimeter-sized chip, something once thought far too big and complex to avoid decoherence, what's the next macroscopic absurdity that we'll eventually understand, control, and maybe even build technology with?
It seems the quantum world keeps expanding its reach into the macroscopic. What's next? Something to ponder.
Indeed. Until our next deep dive.
We'll see you then.